Okay, in the first 5 minutes or fewer, I'm just going to talk about the last bit that we talked about last time, right? I promise I'm going to trace the code a little bit with you. It's kind of very low-level code, so I just want to give you just enough idea about how you may want to implement scanner from DFA if you want to. But in practice, you don't have to, but at least get an idea about the detail. I'll just trace one of them and give you some insight, and then that's it. And then we're going to move on to Parser. Okay? Basically, if you review the last part for the lecture from Monday, okay? Basically, we say that once you get your, given this particular regular expression over here, you will get some DFA that's minimized, okay? Let's say we got that. In this particular implementation, you will get 3 kinds of tables over here, right? Transition table you know pretty well, but now notice that you only got 3 columns over here. Somehow it has been abstracted a little bit. So you can see digits over here simply means anything that's between 0 and 9. So that's more like an indirect lookup, just to save the space a little bit, okay? And then also you got the type. The type is very, very important. It's about the syntactic category of the token you're going to return, okay? So these are the 3 tables. I want to trace a little bit, not necessarily line by line, but just show you how you can run it, okay? Basically, you're just going to initial state will just be S0. Okay, we start with this particular guy, S0. Okay, and the word is just going to be whatever we have read so far. That one's easy. And there's going to be a stack. So let me just put S over here, stack. It's going to be pushing, keep pushing state. Initially, just going to be bad. Okay, think it this way. Eventually, we're going to, if we have to roll back, if we keep rolling back until we see the bad, that means the string should not be accepted, something like that. Okay. So now we're going to show you how you can do a paper lookup. So here we're saying that while the state is not equal to error states. So SE simply means error states. And then tell me the next character to read. In this case, we're reading the first one. So next character to read should be R. Okay? So now think about the lookup. Basically, first of all, the state currently is simply S0. It is not accepting according to our DFA. You can look it up. Just see very quickly. Okay, so now we're going to bypass. And then you're going to say S.push the states. So we first of all push S0 over here. Okay? And now, how do we do transition? That's kind of the indirect part I want to show you very quickly. First of all, we want to see what's the category over here. So that means the character is simply just over here, R. According to the category over here, R is simply just register. Register. And now, when you go over the transition table, state is currently S0, and then you go for the category, which is register, and you get S1. Okay? It's a little bit indirect, right? Rather than saying just go with just the R directly. Okay? So now, after that, you will simply get S1. So state will just be S1, and then keep going through the loop. Okay? Of course, you're going to push S1 over here. Keep doing. So you're going to get 2, 4, and 1. Okay? Until the end, it is more like end of file, basically end of the input. In that case, it will just be other. Okay? So then, and then once you get other, eventually what you will get into will be some error states, basically. Okay, I wouldn't trace the complete details. Once you get to the error states, so that means we have to somehow, okay, let me just trace a little bit further, sorry. Let me just do second iteration. So now let's say we are now currently in S1, let's say. What's going to happen if we read a number? Let's, for example, let's say 2, right? In that case, when we go to the loop for the second time, right? So what's going to be the category over here? It's going to be digits, exactly, right? So now think about 2 is the next number, so that would just be a digits. So now, let's say we are in S1, we are reading a digits. In that case, we are just going to S2. Okay, so S2 is going to be pushed over to over here. So keep going, okay? So now, eventually, we're going to reach end of file, right? That's what we're going to reach. In that case, it's going to be other. So now, S2, other, you're going to go into error states. Okay? So now, to be more precise, 2, 4, and 1. So S2, S2, and S2. And now we got SE on top of the stack, basically. Okay? How are we supposed to roll back? So now, once you go to this particular while loop, you're basically just going to, so far, what we have read was R, 2, 4, 1, and also implicitly end of file. That's what we have read so far. right? So now we have to roll back to say, once we include end of file, it's not going to be a valid state. So we're going to roll back. So keep popping off the stack, and also keep truncating the word. The first one we're going to do is truncating end of file, and also pop off this guy here. As soon as we have done that, we're going to see it's going to be S2. So now S2 is going to be the state. It's now accepting. So that means that'll be the longest string that's going to match the pattern. Okay? So that means eventually we're just going to return R, 2, 4, and 1 with a category. Okay. It's a little bit tedious to do. Basically, you just got to go and keep some stack and then roll back when you reach the error state. Keep going like that. Okay. Do you have to implement this on your own? You don't have to because it's already done by you. Just give you a little bit of detail here. Okay. Any question about this? We okay? Yes, Raymond. Yeah. Oh, because if you look at, I didn't really show in this detail here. By the way, S2 is one of the accepting states.
Oh, okay.
It is.
It shows you right there.
Oh, exactly, S2. Yeah.
You wouldn't actually have that stack because every time you're at S2, you're going to reset the stack. Like you reach S2, it's 1, and then the next stage you read the next character, which is like 4, and you reset the stack now.
Yes. So, yeah, maybe some detail I should really I should really present. If you reset a stack, let's say you reset it, you still get an SE. So I think, you know what, that's kind of interesting.
But you end up with, even if you put the bad, you end up with bad S2 SE eventually.
But,
And then you'll pop up the S2, you truncate the last one, which is the EOF, you exit because then the next one will be S2, S2, not an F will be false, and then if S2 is an F, that will be true, and then you'll return.
wow, it's
So it'll work, it's just, it'll be
Yeah.
acting out the standard.
Yeah, okay, you know what? Let me delay this a little bit. I should have rehearsed a little bit myself. Okay, how about this? I will make sure I do a 1 minute correct version with you, just one more time on Monday. Okay, otherwise, Okay, but the idea will be you don't have to write this code yourself. Just understand roughly what it is doing. Yeah, go ahead.
Can I ask something about the intuition? What is
Go ahead.
I don't know if you know,
Yeah.
know the answer. What is the intuition behind the resetting the stack when the state is during the reading?
I think this is how I understand it. If you got a long string like this, okay, sorry, or I can find the answer over the weekend. If this is your string, let's say, maybe up to this point, you already get to the one of the accepting states, let's say S2, okay? And then, up to here, you already reach S2. The idea about resetting the state is to say now, we want to find the longest one, so we want to expand further. So now, basically go further, and then go to the next one. Maybe go until you get to the next S2 over here. In that case, maybe this is the one to really read over. So now eventually we'll accept the longer string like this. You know what? Let me think about this question here to give you a better answer. So I believe resetting the stack has to do, you want to match the longest matching pattern possible. It could be that, yeah, maybe also for memory concern. Yeah.
You'll always match because you go as long as you're not in the error state.
Let me find it out if I can find a satisfactory answer for everybody. Okay? Yeah. I don't have an answer for now. I will find it out. Yeah. As I said, this code here just gets some intuition, but of course you haven't got the intuition yet. I'll try to revisit this. Yeah. When I was reading this code, it seems quite obvious to me, but there's some little detail I didn't catch. Okay. Okay. Let me come back to this on Monday. Only 1 minute. Okay. So the next topic will be about parser. But do you have any concern about scanner in general? The stuff we review? You okay, right? Okay. So what I will do now is about the next topic. So maybe for today and also part of Monday, we have to review context-free grammar, maybe parsing tree, and do some examples. And then later on, we're going to say something new to you. We're going to see how we can do the so-called top-down or bottom-up parsing. And think about what might be the parsing error you might get in the parsing stage. But that's something we'll get into. Okay, let's review quickly. Okay, but the slides is there. Okay, so this is kind of the context over here, right? The diagram. So we have done this particular lexical analysis. Let's say we got some scanner. right? The scanner is going to give you a sequence of tokens, right? And then, so now we're going to say we don't really process the input file character by character. It's not going to be token by token, okay? And then, how do we group the tokens together? We need to have more like a recursive structure for the tokens. That's going to be a grammar, okay? You can see that. But the idea will be the output from the syntactic analysis will be some tree, like a parse tree. That's something we'll see. So later on, when you do the more interesting bit for the compiler, you're going to do lots of tree traversal and tree reshape. That's basically the idea. Okay. So now let's see this. Okay, what you got from the scanner will be a sequence of classified tokens and words, like maybe keywords, maybe identifier, or maybe while loop, etc. Right? Different categories. Okay, and then now we have to learn. We have to review about how you can write parsing rules for parsing them into abstract syntax tree. Okay, that's something we're going to review quickly today and maybe on Monday. Once we terminate, we have to see if the input string of input sequence of tokens can be parsed into a tree. If you cannot, you got to report errors. If you can be, you got to do further semantic processing. And then AST, abstract syntax tree. We'll see lots of examples for abstract syntax tree. Raymond, questions? Yes, correct. Think about this. It's like reading an essay. The way you read it, the first pass, make sure every word individually in isolation is spelled correctly. And now you worry about grammar. Yes. So we don't consider every character in input program, rather groups patterns of characters. And now we're going to see context-free language. Okay. Basically, I'll just mention very briefly in the next slides, the kind of language we want to handle right now cannot really be handled by regular language, simply because they are recursive in their nature, because it can be infinite number of possibility that you simply cannot memorize using the states of DFA. Okay. Okay, context-free languages. So we have seen regular languages. We have seen finite automata, regular expressions. The only thing we didn't review is a pumping lemma. You may have seen that, but let's not worry. I just want to mention that here. Okay. If you want to prove that a language is not regular, you're going to do something like a proof by contradiction using pumping lemma. But let's not worry about it. So now languages with a recursive structure, they will be non-regular. Okay. So for example, this might be the very classical example you will see, right? Like a hello world example for regular, for non-regular language. So this one can be easily specified. Well, first of all, get some intuition. Why can this not be recognized by any DFA? That's true. That's true. Yeah. For example, over here, let's say I'm drawing something on iPad. I'll switch that. Okay. Okay. Let me see. Okay. Consider this particular potential solution. Do you think this is corresponding to 0 to the n, 1 to the n? Okay, hopefully you can see that at least. Convince yourself this is not going to solve it, right? Because the problem is you just cannot actually keep track of how many you actually have got. If you read, but n can be arbitrarily large, right? If I know n is somehow bounded, you can have a DFA for that. If it is not bounded, you just cannot have that many states. It's just infinite. Okay? Good. Okay, that's just quick intuition from 2001. Okay, so context-free grammars. So we want to describe string patterns in a recursive fashion. You're going to see that. And then context-free languages will be that's something that can be described using CFG. We'll talk about formulation for context-free languages, maybe a later slide. We'll see examples first. And then it's a proper subset. So what do I really mean? I'm pretty sure you have seen diagrams like this. Simplified version. If you think about these are all the possible regular languages, and context-free languages seem simply a strict, like a proper superset. For example, one example could be 0 to the n and 1 to the n, right? Okay. Okay. Now, example. Okay. Easiest example. Okay. You know what? For this one, I don't even bother to let you try. Okay, that was too easy. But I just want to review a little bit terms, okay? And then we'll try something slightly more tricky, slightly. Okay, that's a grammar, just notation-wise. Okay, let me just look at that. I'm pretty sure you can convince yourself why it is working. What I want to do, I'll put it on the iPad, and then I'll just want to explain a few terms so we are on the same page. Okay. Okay, that's the context-free grammar we have. Okay, so now, so each one of them will be a single rule. So we simply use arrow. There will be some cases where the same. Okay, first of all, I'll talk to the simplification in just a moment. On the left-hand side, so these are the variables, right? Or non-terminals. So these are more like a recursive cases for your generation. Okay, and then on the right-hand side over here, so now, so this is more like a single token, like a valid token. It's more like a single word. So this will be the base case. Okay, so in order for me to see exactly what languages might be generated by this, let's see just one example, and then we'll see more complicated one. So now, first of all, is 0, 1 a string of this language? I heard no. You should have a star at least in the middle, right? Okay, good. 0, 1 is not in this particular language, okay? Not in the language of this, right? Think about how we're going to generate. You have to start with some, and usually you would say which is the start variable. In this case, it's A, okay? You have to designate one of the variable to be the start variable, okay? So I will start with A, with a variable, and then when we do the derivation, something called derivation, we'll talk about a little bit more next time. Derivation is going to be double line arrow over here. So now, start with A. I can replace A by 0, A, 1. However, this is not a string just yet. A string is defined as every character there must be a terminal. But now, A is not a terminal, so we're not done yet. So now, we can terminate right away. We can simply say this is simply, and replace A by B, okay, 0, B, 1. Not terminating yet, right? And then we can say now B can be hash. So 0, hash 1. That is a shorter string you have. This is a derivation. Now, how do you draw the corresponding parse tree for that? Okay, that's something we're going to review as well, okay, just quickly. If you can draw the parse tree for a particular string according to the grammar rule, that means the string is valid, okay? So now for this one, according to this, A may be replaced by 0, A, and then 1. And then the A over here may be 0, B, and then 1. And then the B over here may be...
No, just me.
I'm so sorry. Thank you. Think about which rule you're applying. So now over here, A will be replaced by B. This is the one I'm applying. Yes, you may. Yes, you may. You may want to generate longer string for sure. I'm just. It will still be a valid tree. It's just different tree. Okay. Yeah. So now A can be B, and then B can be hash. Exactly. So now to see the string, you just look at the leaves together. Okay, 0, star 1. Okay. 0, hash 1. So one possible question, well, I'm not too sure. That's maybe too simple. Could be I give you the grammar, and then simply ask you whether this is a string that's valid, that's in the language. How do you show it? Draw a parse tree, or just show some derivation. Okay. Okay, that's a simple one just to review some terms. Okay, just make sure you're familiar with the terms. And then we'll go with another one. And this is simply just some process about how you generate production. It's just a little bit more description over here. You can read it over. Okay, it's a quick review. Okay, so now, of course, you can get infinite number of possible strings. Okay, so these are just more examples I already showed. Okay. Okay, and also parse tree. Okay, that one is there, just a little bit more complicated than the one I showed. Okay, also convince yourself. You don't really have to draw like this. If you draw the branch is not as long as this one here, that's fine too. Okay, Raymond, question?
Generate a parse tree for every string. That's what we're doing.
Basic, okay. For the compiler, yeah, given a string, it will try to figure out somehow to see if it can generate a parse tree for, okay, think about the overall picture. We'll see more details later. Basically like this. Think about parser over here, parser. And then it's going to be a sequence of words over here. And then you either say yes, the sequence of words is a string in the language of the parser. In that case, you're going to generate some AST, some parse tree. Otherwise, you're simply going to say just no. And something will give you a little bit more detail. For example, if you try something like this, I guess, if you try in Java, you can say if maybe true over here and brackets. It might show you there's some syntax error in the token. Maybe the curly brackets, the closing curly brackets. Similar idea. Okay. Okay, and then the parser, of course, itself, because the context-free grammar that we're going to specify. Okay, so now let's go a little bit further. Palindrome, are you okay with that? That one's easy. Okay, I'll maybe save only one of them for you to do exercise. Basically, palindrome, the word will read the same, forward and backwards. And remember, we did it in 2030 when we talk about recursion, right? So that's exactly the kind of recursive problem we can solve. Okay, it can be epsilon, that's the base case. And then it can be 0, it can be 1, or it can be 0p0. Okay, that's easy. Oh, also 1p1, of course. I forgot to show that. That one is easy, okay. Do you think this might be the same?
No.
Not quite the same, right? It's not really palindrome, right? How would you define this a little bit differently? Oh, reverse. So W followed by the reverse of W, basically.
You'll have to have another variable.
Actually, it turns out to be possible. Turned out to be. Why don't we have a look? Okay. This one I still consider as easy one. I'll leave the slightly harder one for you. Okay, these are some examples. For example, you can see over here, 0, 0 for short, because 0 is a reverse of 0. And also 0, 1, 1, 0. Once you see the example, hopefully you can see how to generate a pattern, right? So you can see 0, 1, 1, 0. Basically, well, hopefully it's quite obvious, right? Because 0, 1 and followed by 1, 0, okay. I would say sometimes maybe the grammar is not so obvious. Maybe try to come up with some example that will help. Okay. Oh, yes?
Is it the same as palindrome?
It's not the same as palindrome. Oh, actually, good question. Basically, it's also a possible question in the future. Okay. For example, you're basically asking the following. We have maybe W such that W is palindrome. Is that equal to the language where W followed by WR? Right? Of course, W is simply sigma star. Are they the same? That's a question. If you don't think that's the same, how do you disprove it, for example, right? You'll simply come up with? Yes, that's true. But just give one conflict. Well, so for example, you would say, let's say if this is L, L1, let's say this is L2 over here. So let's say, again? Oh, yeah, actually even 1 would be fine, right? Okay, sure. Yeah, 1 is a member of L1. Yeah. And then 1 is not a member of L2. Right? That's one example. So Raymond, they are not the same. Yeah. Make sense to you? Another case would be, let's say 1, 0. Oh, actually, no. Think about some cases yourself. Okay, so now that's also considered as easy. Okay, also grammar rules different. Let me see if I can get to the, how about this one here? This one requires a little bit of thinking, but it's not too difficult. Okay. Let's say we want to have a context-free grammar for binary string, so alphabet 0 and 1. Okay, and we want to say somehow you can divide the string into blocks of zeros and one. And for every block, you want to make sure zeros are followed by at least as many ones. It cannot be fewer. Example could be, let's say, for example, here, right? This is one block of pure zeros, 3 zeros. Now I follow by 3 ones. That's as many. That's good. I can also say 0, 0, 0 followed by 4 ones. So that's more than what's in the 0, right? So that's also fine. You want to try to think about it? We can try some answer from you. Okay, let's just do this one together. Okay, I do have solution there, but you might come up with something different. Yeah, so for every pure 0 block, you want to make sure followed by at least as many ones. You may want to think in this way. Is it possible to have a pattern where you got a block of 0 followed by exactly the same number of ones, and then build on top of that to make just more ones? So that means you might need more than one variable, right? For different cases. I'll present to you maybe just one possible solution. If you come up with others, you're not too sure, you can also check with me later. Okay? Okay, I'll give you 1 more minute, and then we'll try to look at that. I would say in general, when you try to come up with a context-free grammar and later for your projects, we don't really check, but I would say try to minimize the number of variables if possible. Sometimes you might find that you can just simplify, collapse certain variables into one. Okay, shall we take a look? Okay, compare with yours, okay? Okay, let's say this. You may have different variable name. Let's say we have variable s to say it's going to be exactly satisfying that. Okay, so s can be divided into base cases and also recursive cases. And then s can be divided into several blocks. Okay, so conceptually, okay, just before I present to you, think about eventually it's going to be s, but it can be divided into a, this is a particular block, particular block, particular block, something like that, right? As many as you like. Now, always think about, can epsilon be included in S? It can be, right? 0 zeros and 0 ones, right? That's always the base case to think about. Okay, so that'll be one base case, okay? And then, let's say, okay, that one tells you the recursive case, which means S can be followed by as many A's as you like, as many blocks. And every block of A is going to be it's going to start with some pure zeros block, followed by as many ones. Maybe exactly the same number of ones, or might be more. A can be epsilon, agree? Just in this block, right? Now, one way to think about it is, let me just show you one thing here. Yep, so you can see A here is another base case. Would you agree this is a valid block? Right? Yeah, just 0, 1, just the same, right, number. And then you put another recursive case. So this A over here tells you got exactly equal number of zeros and ones. But now we are not quite complete yet. So far we have done with exactly the same number of zeros and ones. But we want to allow, you can add more ones, as many as you like. How do we build on top of that? 0A11? That's one way to go. Yeah. So what Raymond said was 0 goes to 0A11, while Ash said was A goes to A1. Yeah. Pretty much the same, yes. Yeah, A1.
Also, your second base case for A1
Yeah.
In the, I'm sorry, just in the example before, do we need to make B hashtag or could we have just made A a hashtag?
You mean the previous example?
Yeah, the very,
Oh, come back to your remark.
sorry.
You're talking about this very first example here, right? Okay, what about it?
Can we just make A a hashtag? Why do we have to make A goes to
Oh,
B and then B?
actually, in this case, yes. I believe the reason the question was, can I simply get rid of B and simply put hash mark over here? Yes, you may.
No, because you always, it's have to be zero, have to be at least 0, 1.
Instead of A goes to B, A goes to hashtag.
Let me see the original definition here. Oh, actually, that's fine. Actually, Raymond, that's okay, because here I say n larger than or equal to 0. When n is exactly equal to 0 over here, so that means we're going to get 0 to the 0, which is epsilon. So you only get hashtag. So that's okay.
Okay.
Yes. However, if I put n strictly larger than 0, then it will not be okay. So it really depends.
Oh, okay.
For this particular language, yes, you can do that. Mhm. And you were saying something like about the epsilon.
I was saying that the current
Yeah, let me
base case was unnecessary, like minimizing set of rules.
let me take a look. Could be. You mean this guy here, right?
No, the second base case. This is the second base case.
Oh yeah, yeah.
Use the third one.
Sure. Yeah. So the remark was this one here. So now, first of all, do we need A is epsilon?
Yes.
We need that, right? Because you should really allow epsilon for sure. So now, given that we have this base case already, do we really need A is a 0, 1? All you got to think about is if I got rid of it, is it possible to regenerate something just would just be 0, 1? Sure. Okay, I'll write it down, the parse tree, and then you can think about it. So A, and then it will simply just be 0, A, 1, and then epsilon. Like that. So that's fine. Yeah, it's kind of additional. Okay. So this is okay. So that means the A is 0, 1. Not wrong, but just unnecessary. Yeah. Okay, any question about this particular problem here? We okay? Just more like a review question here. Let's consider something that's a little bit related to programming languages. Okay? Let's say we want to design a grammar for some small expression language. Let's say we want to have arithmetic operations. We got multiply, plus, minus, multiply, divide. Also all the relational operations, also all the logical operations. And of course, true and false, they're not really operations, just literals. I just put it in the same category. Okay? I'm going to present to you two versions of the grammar. And then we're going to discuss a little bit what will be the difference. Okay? Let's see. How about show you the grammar right away? Okay? Maybe that's easier. Okay? And then we'll talk about what might be the pros, might be the cons. And we're going to assume that the star variable is going to be expression. Okay? And then, okay, I'll get back, you can read this remark a little bit later, but I'll definitely talk about it as we go. Version number 1. Let's say for expression, it can go to integer constants, or it can, when you use the vertical bar, it's simply alternative. So you don't have to say expression produces integer constant, and also expression produces Boolean constant. You can use just a single. You can use a properly aligned vertical bar. That'll be fine. So expression can be either integer constant, Boolean constant, binary op, unary op, and expression. Pretty easy. Okay? And also integer constant can be digits. Okay? And then minus digits, Boolean constant. True and false. Okay? So far so good? Okay. And then I will go to the next, only 2 pages for the version 1. For the binary op, I say it's going to be all the arithmetic. Also, it's going to be all the logical. Also, all the relational. In some way, I'm putting them in the same category. for the grammar. So they are all considered as expression. In some way, if I say something plus something, it belongs to the same category as something equals something.
Okay, what if you expression is Boolean plus another Boolean? Does it make sense?
Yeah, okay, you're basically pointing out what the problem might be for this particular grammar. Okay, Kelsey, question.
Do you want to separate this into arithmetic and logical expressions?
I would.
Or does this stage of the compiler kind of like do this
Whether your compiler deal with, okay, first of all, it seems that everybody already pick up some problem that's quite obvious. Okay, okay, that's the whole definition. Okay, let me just write down the string you're talking about, and then I'll get to your point. Okay, for version number 1, will everybody agree? I can write something like this. Yeah. I'll write 2 examples. Let me switch to iPad in just a moment. First of all, would you agree? Oh, actually, I do have that in my iPad. I forgot. Okay, I forgot. Okay. So now, would you agree? Okay, that's version number 1. Okay, would you agree? Do you think this will be a valid string in the grammar?
A string, yes, but not.
Oh, or let me put it a little bit different way. Can you draw a parse tree for 3 implies 6 for this grammar? You definitely can. Easy. Want to try? I'll just try the first one. Okay. Let me just say E for expression. We'll start with the expression, and then which rule should I take? Binary op. Binary op. And then expression implies expression. Thank you. And then integer constant, right? Okay. Yeah. Good. Good. Yeah. Integer constant, and then digits, and then 3, right? Integer constant, digits, and then 6, right? Easy exercise. Okay. So 3 implies 6 is actually a valid string by the grammar. But remember, it's context-free, meaning that it only talk about structure without worrying about whether the kind of operation you're doing semantically makes sense. So that means it's subject to some semantic analysis or type checking. So I'm just saying version 1 is actually one way to define your grammar, given that you're actually going to do some semantic analysis like a type checking later. Okay, make sense? Okay. Nothing wrong with this. I'm just saying that's one way to write a grammar, but you got to be clear. These are possible strings. Okay, that's one problem. Problem number 1, you can allow something that simply doesn't make sense. Okay? Well, how about this guy here? Anyone else? The question was, if you look at version 1 of the grammar, right? We said that one category of the flaw was, well, not really flaw. One issue over there is you can have things like a 3 implies 6. That doesn't make sense. Another one, if you look at 3 multiplied by 5 plus 4, do you see what the issue is? Yeah. Yeah. It seems like order of evaluation. Yeah, somehow precedence is not really specified over here, somehow. Okay, so now I'll just do it just enough. So this is one witness for the grammar being ambiguous. And if you recall, can you recall what does it really mean for your grammar to be ambiguous back in 2001? Exactly, for the same string. If your grammar is not ambiguous, you should have a unique parse tree. But now, for the same string, we can have 2, well, at least more than 1 parse trees. Okay? Exercises for you. Okay? Exercises. Draw all the possible parse tree for this string. This string here. Okay. For example, if I simply ask you what is the following grammar ambiguous, that's how this show one witness, right? For which you can draw more than 1 parse trees. So that's ambiguous. Okay. So at least 2 issues over here. This issue is definitely more severe than this, because for this one, you can definitely try to compensate for that by doing some further semantic analysis. That's okay. But this one here is simply just not certain how to do the order of evaluation. Two ways to resolve this. Number one, you can try to introduce maybe a little bit more terminals to actually specify the precedence. We may not see it today, but we might see it a little bit later. Okay. Number two, when later on when we see the Untitled tool, you can actually somehow specify the precedence for the operators. That might be the easiest, the most convenient way for you. So when you specify your parser generator later, which we'll see later, in that case you can say multiply and also divide should actually come before plus and minus. Again, the higher they are, the higher precedence they are. Okay. So either way, either you can change the grammar itself, or you can simply specify that.
But it allows us to do half the same.
In this case, yes. I'm just saying for this particular rule.
So we can actually specify that?
You can do that, yes. Yes, I'll try to make sure I cover that in the tutorial, yes. So you can, so you can definitely specify that. I forgot exactly the keyword you had to say. Maybe you have to say something like a precedence and then put the operator afterwards. Yeah, I'll make it clear later. Okay, that's about version 1. Okay, let me see if there's anything else I want to say about version 1. Okay, that's something we said already. Let's talk about version 2, okay? Let's see version 2. We are basically introducing a little bit more a little bit more non-terminals, okay? Arithmetic operation, relational operation, rather than just expression, right? And also got logical operation and also expression. Okay, you got parentheses. Okay, you got digits, the same as before, and also got Boolean constant, true or false. That part is the same. The main change was about the operation here. Okay, and then let's say this. Well, you may just realize. Do you think we may have resolved the ambiguity issue? Not really, actually, because now I have not. Well, still you can see plus, minus. Well, especially let's say plus and multiply. They still belong to the same grammatical category, like arithmetic op. So I have not solved that issue. Just not something to know. Okay, it's not the point for this particular example, right? What I want you to compare is from version 1 to version 2. What's really the difference? Okay. And now integer constant over here, relational operation, logical operation, basically just more categories. Should you go for version 1? Version 1 and version 2, they're equally bad in the sense that they are ambiguous. But there's some minor improvement from version number 2 in some way.
One remark is not even related to these.
Sure.
You can actually do like 3 minus 5 with the integer constant based on how you specify. If you go to the previous slide, you can actually do like 3 minus 5. Sub in digits, integer constant, and then integer constant, negative integer constant, and then digits.
You mean 3 minus negative 5?
Yeah, no, 3 minus 5 is 3 minus 5.
Uh-huh.
That could be considered an integer.
Integer constant over here.
Because you could, at the first step, replace it with a digit integer constant.
Oh, interesting.
Yeah.
Yeah, sure.
That's like a weird.
That's a bit weird, I agree. Yeah. So what he's saying is, sure. If you look at version 2, if you look at that, let's see this. Yeah, the same. So now here, let's say the digits, integer constants, and then I might have digits, and then followed by integer constants, and then I can say this one simply digits would just be 3, and then integer constant over here, it can be minus integer constants, right? And the integer constant here can also be a digits, and then it can be just 5.
Would it be flawed because it being minus minus 5?
Yeah, you can also do stuff.
Yeah, something like that. Apparently, that may not be so intended by you as a grammar writer, right?
So realistically, what if we just do integer constant goes to a regular expression, like where? Because I'm saying like you can easily use a regular expression to.
You may.
Integer constant and then do that.
You may.
Instead of
Sure.
trying to do
Yeah, I would say usually for the number pattern, you might just use regular expression. Yeah, for this one, you don't show something here. Yeah. Okay. For version number 2, we want to consider different points over here. Okay. Let me just before I come to this point here, you want to convince yourself this particular grammar is still ambiguous, because over here you still have maybe plus and multiply in the same category, right? So you can still draw more than one parse tree for this particular one. Okay. So exercise for you is to draw the parse tree. Okay, and now let's look at other example. Now, if I try to give you this input string, will you be able to generate a parse tree for that? According to version 2 grammar. Any idea? By the way, this string here would be accepted by version 1, because everything is like an expression, right? Like binary operation, right? But now, will this be accepted? Okay. Yeah. Basically, think of it this way. Okay. You can think about one way. Well, the only way to generate this. Well, if you try on the way to generate that, you can start with implication, right? Implication will be okay. Start with expression first. Okay. That will be the flow. Start with expression, and then implication should be logical operation. And then for logical operation, you will go for implication. However, now the left and right are required to be logical operation. Can you ever derive 1 plus 2 and 5 divided by 4 using logical operation? Not really. So this string over here would be rejected by version number 2, but it will be accepted by version number 1. So in some way, we incorporated some extent of type checking in the grammar. Okay? Is this what you want? Maybe, maybe not. I think it depends. One way of doing it is you don't try to do any kind of a logical, don't do any kind of a semantic analysis. Don't encode it in your grammar, and just do the easiest form, just expression, and then do the semantic analysis later. That's one way. Okay. So now, apparently, this is one issue over here for the grammar, right? This one, it looks like, for example, if you got 3 minus 5, it's not really like a 3 subtract 5. It's not really according to the grammar, right? So that's definitely one string we don't really intend to have. How about this string here? Do you think this string might be okay? The same thing, right? Okay, good, good. Is there another example I want to show? I think, you know what? I might have just made a typo over here. I beg your pardon. Can I just change that right away?
Yeah, remove the brackets would be even more.
How about that? Is this string okay? I think maybe that's what I meant to put.
I think that's, yeah, you can do it.
You can do that, right? Okay, so now I would say this one can be a little bit of debatable. Okay, first of all, let's agree. You can definitely draw a parse tree for this. Number one, we agree. This is a valid string.
Yes.
Because you can draw a parse tree for that. And now, if this is somehow accepted, I think it will be up to you as a compiler writer to decide whether you want to generate compilation error, or you want to simply go to the runtime and then have some division by 0 error. Typically, like in Eclipse or in Apple Studio or other, Visual Studio, they don't usually tell you you might have the potential of having division by 0. But it doesn't really stop you as a compiler writer to say, maybe in some simple cases, I can attempt to evaluate the right-hand side of the division. And then I'll try to see if I can evaluate it. If somehow evaluate to maybe 0, in that case, I want to use the right away to tell you, oh, be careful, this might be 0. In general, yes, you cannot evaluate, well, especially once your language gets more complicated, you got method call or even loops. Yes, for sure. But you can attempt to do it. If you cannot. Mm-hmm. Well, some integer constant and some expression over there, right? Mm-hmm. But for this particular small expression language, right, that will be your choice. Whether you want to really report a compilation error because you will get division by 0. It's up to you. Mm-hmm. Yes?
I guess just from experience, I'd rather just use the runtime error for everything because it's like you don't want, if you have a more complex language, you wouldn't want to see that method calls that result in division by 0 are runtime error, but simple expressions that result in.
Yeah, sure. Because simply because usually the language like a Java or C# or Python, they're complex language. So in general, it's just not possible to evaluate the divisor over there, right? But I'm just saying for this particular small language you are going to program, you do have the choice to tell the user, well, you write something here, but it's not gonna run at the runtime, right? Okay, depends. Okay, good. Okay, so now let me see anything else to say. Okay, so my point is, it would be your choice. Report this as a compilation error, if you wish. Yeah, it could be error, it could be warning, depends, right? Because it's gonna fail anyway at the runtime, so it could be considered as error.
Well, it's like
Why would you want to do division by 0?
Java, for example,
Mm-hmm.
causes a division by error. You can actually throws an active exception and catch and then recover from.
Yeah, but still, why would you want to do division by 0 in the first place, right?
Like for example, your
Mhm.
program could be reading input and not checking and directly divided by it, but then in a try to
Mm-hmm. Yeah, but in that case, of course, if you only read something from user, you cannot really tell, right? You kind of Yeah, I'm just saying. Yeah, I'm just saying not in general, but for this particular small language, there's a choice, right? Yeah. I'm not saying if you're given a language like a Java to program, you should really definitely check it. Just for this particular small language. Yeah.
Just check.
Yeah.
If you do the optimization, then what would the C++ it actually changes the evaluates them?
Oh, sorry. Can you say that again?
If you turn on the optimization,
Yeah.
the pilot actually evaluates that before the
Oh, you mean for C compiler? Mm-hmm.
They evaluate integer constants.
Okay. Mm-hmm. Sure. Okay. So, right. Let's see what else. Okay. Let's go over a little bit more slides over here. Okay. Okay. So now the important thing is to see that version 2 is also ambiguous. Okay. So later on we're going to see how we can resolve ambiguity. Right. You want to be careful. Okay. Okay, formal definition for context-free grammar, just very quickly. Okay, so now just like how we formulate DFA, NFA, it's going to be like a tuple with critical components. So we'll just go over it quickly. Okay, you got variables, non-terminals. Also, you got terminals like tokens, and they should not be the same, right? The intersection should be empty. And now, so these are simply just rules. Don't be too terrified by that. So it simply means the rules will just be a set of from variables into some string. And the string will simply just be, how do you read this? This expression here, how do you read it? Does it tell you that you should have variables only, or you got terminals only, or like a mix?
Any amount of variables
Then you combination.
Yep. Basically, this one tells you it can be epsilon, for example, right? Or it could be no variables, but only terminals. It can be no terminals, but only variables. Or it can be a mix, right? That's why we simply say, take the union of the two sets and then take the cleaning star. Okay, also we got star variables, okay? Usually just one. And now we want to talk about rule. Whenever we talk about rule, just derivation. So now let me just go to just show you how you can read math quickly. Sorry. I'll switch the iPad in just one moment. Okay. UAV UWV. Basically, you can go from here to here. You can see the only change is from A to W. So that means you got some production rule. A produces W, basically. Okay? And now the W itself, again, it's just a production rule. It can be a base case where you got terminals only, or it can be some recursive case where you only got variables, or maybe a mix. Okay? Just basically what it is saying. And then just go a little bit more, and then you say this one here is telling you put a star here. That means you can take some finite number of steps to go from U to V. Yeah, that means you got some. If you can go that, okay, let's go. That's kind of recursive definition over here, right? So that means you can eventually go from U by a finite number of derivation and go to V eventually. Okay. A yield sequence. Yeah, they also say something yields this particular right-hand side. Okay, finally, that's the set comprehension we to review. Okay, so now let's say, how do you read this? The language for the grammar would be all the strings W such that what? Yeah, exactly. That's something you, that's exactly how we draw the parse tree, right? So starting from the start variable S, and then you can take as many derivation steps as long as it's finite, and then eventually reach W, right? It's not such that W is terminals only, just a word. And notice that W is just a sigma star, okay, over here. Okay, just this slide, a little bit just a formulation about what we said before. But for this select course here, don't worry, we don't have to review pumping lemma for context-free languages, even though it's interesting. Okay, okay, let me see what else. Example. Okay, how about just last example for you to try? And then we'll continue. We'll continue with some new stuff, hopefully. We still got a little bit more slides, but they can be done very quickly on Monday. But we'll definitely get to some new stuff. So now, when I say present your answer in a formal manner, think about what should be the start variable in your grammar, and what should be the alphabets, and what should be the production rule, basically. Properly nested parentheses, right? And notice that it doesn't have to be complete nested, it can be parallel as well, right? You can see this pair followed by another pair over here, okay? Yeah, this one should not be too difficult. When you're done, and then let's check your answer with a slide, and then we're done, okay? All right. Let's take a look quickly. Okay, so now basically you can see the whole G, the grammar. So start variable is simply S. And then the alphabet would be opening parentheses, closing parentheses, R, which will be defined as follows. And then S will be, I forgot. S, sorry, beg your pardon. Let me say that again. We're saying that the only variable you have in the grammar is S, where S is just a start variable at the same time. Okay, good. Okay, so now that's a grammar. Okay, double check for yourself if that's okay. Notice that if you leave out SS, would that be okay?
Can we can we change SS to like parentheses S, like open and close and then S?
It would not be necessary though.
Oh.
What Raymond's question was, let's think about it. The question, okay, let me put it down. But it would be nice to know about why it wouldn't be. Raymond's question was like this. Do you think it would be necessary to put this guy here?
Oh, I'm sorry, sir. I meant instead of one of the S's, instead of the S on the left, just put the closing parentheses. And then take away.
Oh, okay, maybe I misunderstood what you meant. Okay. Sorry about that. Okay. Let's say that's the original one. Can you say your suggestion again?
Oh, instead of SS,
okay.
Just one S, and then parentheses next to it, like open and close parentheses.
Well, no.
Yeah, this one here is a little bit restrictive, right? You're basically saying you're only next to this particular guy, but this guy here is not nested. Yeah, so that one is not that great. So one potential question you want to think about is, if I describe a language and then give you a grammar, I'll simply ask, do you think the language grammar will produce exactly the language, right? Find some witness. Okay. S can be empty, just no parentheses over there. Yeah. Okay, any questions about this? Okay, you might find some examples in the textbook about grammar and etc. Okay, we'll try to cover some new stuff from next time.